All right, so today we'll talk about the addressing modes. So we probably don't understand what it is right now, so which is normal again. So let's first look at something about the microprocessor. Since the microprocessor is heart of all the digital devices, it's actually a central processing unit, okay, of all the microcomputers and the digital devices. So this is actually a very simple, very small circuit, but which is so integrated that if you really want to build the digital circuit in your breadboard, this room may not be enough. So there will be so many circuits and connections, but it's made in an integrated manner. So that's why it's a single integrated circuit, which looks very small, but there are huge volume of circuit inside the microprocessor. So there are plenty of models of the microprocessor. So it starts from all the way from 4-bit to, as of today, we have, I think, 128-bit. So basically those, I think 64, the ones that you have here is 64 bits. That means that the microprocessor these days can add two 64-bit numbers. So each number is a 64-bit long, and it can add two 64-bit numbers, okay? Which actually also tells the power and capability of microprocessor. That's why a lot of times we define the microprocessor in terms of the bit. We just say, okay, this is a 32-bit version, or this is a 64-bit version, because that makes a lot of difference. Okay. Now again, in this class, we'll not be running after the speed of the microprocessor. We don't care the speed. The idea of this class is to understand how the microprocessor works. So if you really understand how the microprocessor works, using just a simple 4-bit microprocessor is still same when you are talking about a microprocessor with 64-bit capabilities. Okay, it doesn't matter whether you have a 4-bit microprocessor, you have a 64-bit microprocessor. The idea of how the microprocessor works are still pretty same. But these days, as you can see, I have written a couple of things, but there are plenty of other things which have microprocessor. So the calculators, personal computers, and there are plenty of other things which have microprocessor. Even a simple printer has a microprocessor. Okay, but they don't have very powerful microprocessor like we do in computers, right? Your cell phone has a microprocessor, which are really, really powerful. Even some of the cell phone microprocessors, cell phone has like more than one microprocessor, right? So, in this class, we'll mostly focus on a microprocessor developed and designed by Motorola, and they call it a microprocessor from M6800 family. That's actually the family of the microprocessor developed and designed by Motorola. Okay, so most of those are 8-bit devices. So basically, we'll be talking about an 8-bit microprocessor. Okay, we will have a small computer with microprocessor installed on that board. Okay, so we'll have our low-level language instructions which will run on that microprocessor to understand how things work. Okay, again, the idea is not to understand how the Motorola microprocessor works. Idea is to understand how the microprocessor works in general. Okay, that means if you understand how the Motorola microprocessor works, it's still the same like the Intel microprocessor or other microprocessor that you see in your computers. Okay, but Intel microprocessor are usually not open for education due to their business restrictions, because they don't want to, release a lot of hidden information. So, but it's still, idea is still the same. So here is a very basic idea about the microprocessor. Okay, this is probably the simplest, diagram you can get about the microprocessor to understand how it works. Now remember, starting from 4-bit to all the way to 64-bit, idea is still the same, because this is what you have. So so this is, let's say, your microprocessor, which is a single chip. This is your memory. Memory means the RAM, right, in your computer. These are the input-output port, which actually, connect you to the outside world, right? For an example, let's say keyboard, right, mouse or printer. Those are the ones which communicate with the microprocessor to get the input, to give the input, or to get the output from the microprocessor, right? And what microprocessor does is microprocessor actually simultaneously communicate with the memories, we communicate with the input-output devices. It also send the instructions through buses. Now this bus means some connections, okay? Now if there are like 8 conductor data bus, that means there are 8 parallel lines of connection, okay? Now think about this. What do you do? Why do you need the 8 lines? So that you can just send 1 byte at a time, because 1 byte means 8 bit, right? So you can send all the 8 bit at once, so that you just have 8 lines. So the advanced microprocessor that we have these days are much more advanced than this one. They have more wider bus, right? More faster addressing buses. Now, if you look at two different things, so if you look at here, right side, these are basically the data bus. These are the address bus. Now, what is the difference of these? Think about this. The microprocessor, microprocessor actually, exchanges data with the memory, right? With the input-output devices. It actually transmits data from one place to another place. But inside the memory, you have plenty of locations, right? And these days, think about the memories. We have like what? We have 16 gig memories. We have like 32 gig memories. There are plenty of memories right now, right? And if you think about the memory locations, one memory location is still just 1 byte. And think about how many bytes you have in a single 64-bit RAM. There are plenty of memory locations. Now the question is, how does microprocessor know what is what? Because you might have, the memory locations are like bunch of locations with all ones and zeros, because inside the computer is all like binary numbers, right? So how do microprocessor know what is what? Because there are so many locations. What exactly happens is each location actually has a unique address. That's a lot of addresses. So for an example, we all live in Memphis, right? But how do people find us? Because we have address, and which is pretty unique, right? Our addresses do not match with anybody else. Same is here in the memory locations. Every location has a unique address. Okay? Now, 16-bit address bus means that to point those locations, we need 16-bit. So you might be wondering that the address bus is even bigger than the data bus. See, the data bus is only 8-bit. The address bus is 16-bit because all the addresses are 16-bit long. Now, what is good if the address bus is long? Now, think about this. Let's say I said you have an address bus of only 2-bit. What happens? How many numbers you can write in 2-bit? Only 4 numbers. 00, 01, 10, 11. That means 0 to 3 in decimal, right? How many numbers you can write in 4 bits? 0 to 15, right? In decimal, meaning 0000, which is 0, 1111, which is 15, all the way from 0 to 15 you can write. So now you see, the more longer bits you have, you actually are able to write more numbers, right? So that's why they end up having 16 bits so that they can have a lot of addresses. Now there is a simple formula which actually tells how many numbers you can write. For an example, if you have 2-bit, you can write 2 squared, which is 4 numbers. If you have 3-bit, you can write 2 to the power 3, which is 8 numbers. If you have 4-bit, you can write 2 to the power 4, which is 16 numbers, right? Now think about if you have 16-bit, you should be able to write 2 to the power 16 numbers, which is a lot of numbers. You can, you can check your calculator. It's a lot of numbers. Now that might be not enough when you have when you have like 64 gig memories. That's not enough, right? You might have seen that at some point when we used to have the 32-bit machines, meaning computers, the computer were not able to address all the locations you have in a 4 gigabyte memory locations, because it was limited up to 3 point something because of those restrictions, because it doesn't have more than that numbers. So it cannot give more addresses. Address was like address finished before the memory locations were not finished. You know what I'm saying? So that's why address buses are longer, because so that you can have more addresses and you can point more locations. Okay? We'll talk about this again. Okay? Just give you a basic idea about this. Applications of microprocessor are huge, so I just tried to limit it. I know that this is not enough. We could have just a single presentation of like 5 hours, and we will still not be done with all the applications. So, but it's mostly, mostly limited to computers, video games, calculators, home appliances, right? And even I would say cell phones. And we also have microprocessor to control the operation of automobile engines. Factories have microprocessor in different machines to monitor and control their operations. And it's actually hard to tell how many places we have microprocessor these days. You may wonder if you think, okay? Now, this is another idea of microprocessor data transferring, that how exactly the data transferring happens. Remember, we are not trying to cover everything. We're just trying to give you a very quick and snapshot of idea that how exactly it works. For an example, let's say this is our microprocessor, okay? And remember, as I said, the address bus is 16 bit. This is actually my address bus. Do you see there are 16 bits here, all the way from here to here? So this is my address bus, okay? Now, in this side here, this is my data bus. Data bus is 8 bit, for an example, okay? Now, this is my memory location. Now, as you can see in the memory locations, these are addresses written in decimal. Now, this is my address 0, this is my address 1, address 2, and you know, we have all those addresses up to address 8, for an example. We have even more addresses. We just wrote 8 here. Now, for an example, if microprocessor can transfer data between microprocessor and memories, that means that microprocessor can write into memory, microprocessor can read from memory, right? Two different directions. Now, how do you know whether the microprocessor is writing or reading? Because of this one single line. If, as you can see from this symbol, if this is 1, that means microprocessor is actually writing. I'm saying reading, okay? If this is 0, because W has a bar, right? That means whenever it is 0, microprocessor is actually writing, okay? So microprocessor is either reading or writing all the time, okay? Based on what you exactly requested. Now, for an example, at this point this is 1, that means microprocessor is in reading mode. That means data is being transferred from memory to microprocessor. That means reading, right? Now, you see here, there are a bunch of memory locations here. Now, which data is being read? How do you know? Just from the address. Now, can you tell what is this address in decimal? Look at this address, this 16-bit address. What is this? All the 0 following by 1, 1. What is that? 3, right? In decimal, that's just 1, 1. Now, what is 3 here? This is my 3, right? So this data is actually being read right now, because the address bus is pointing to 3 and it's telling, okay, I want to read 3. That's what I'm saying. Now what we have in 3, 0, 0, 1, 1, 0, 1, 0, 0, which exactly is what will be read here, okay? So I'm saying, I'm just trying to give you an idea that how things work. So what happens is, between the microprocessor and memory, there are several connections, right? One connection tells, okay, I'm going to read or I'm going to write, based on what you need, okay? Now, if you read or write, no matter what you do, you always tell, okay, I want to read this address, or I want to write into that address. So you always send the address to the address bus. And from the data bus, data actually transfers either from microprocessor to memory or from memory to microprocessor, based on what you need. And remember, all of this happens because you requested something, because you wrote an instruction which is being executed by the microprocessor, because microprocessor doesn't do anything by itself. It actually always follows the instructions you have written. You might be wondering, why did I write the instruction? See, all the instructions are written in all the software. For an example, even if you are using a cell phone, you are using plenty of different apps. So what do you have in those apps? A bunch of instructions, right? And every single time you like tap something, you scroll something, microprocessor is getting all the instructions and is actually executing all the instructions. You may not know even how many instructions is running just for one single tab. If you just click one tab, it might be running like 25 lines of instructions. See, the microprocessor is something which cannot do a lot of things, because if you think about the arithmetic operations, you probably remember in probably digital circuit class I mentioned that all the microprocessor can do only one single arithmetic operations, which is funny, which is addition. Every single other operations it does, like subtraction. Remember, we learned subtraction in terms of 2's complement, which actually does addition, not subtraction, right? Remember? So microprocessor can also do some logical operations like comparing two numbers. But you might be wondering, how do the whole world is running only on microprocessor? Because whenever you are like doing, let's say, some multiplication, the multiplication is actually done in terms of addition. Right? Let's say if you do 5 times 2, what do? You are just adding 5 twice. Okay? 5 times 3, you're just adding 5 3 times. So you know multiplication can be done in terms of addition. But this is how microprocessor actually beats us. Microprocessor only knows how to do the addition. And everything it does, arithmetic operation it does, actually does it in terms of addition. But it does those so fast that you don't realize that it's actually doing only addition. You see what I'm saying? For an example, think about microprocessor, the fastest microprocessor in this world. It might be doing like millions of addition in 1 second. Everything is right, correct. Now the thing is, it does it so fast you might be you may not even realize that how fast it's actually working and how fast it's actually doing the addition. So the only way the microprocessor actually beats the human is the speed, nothing else. Because it doesn't know more operations than the human being, it knows only how to do the addition, how to compare some of the basic things, but it does it so fast, you don't realize that it's actually doing only the addition. Okay? So, in our microprocessor, now we are very specific to the Motorola 6800 family of microprocessor, which we will be exploring for this whole semester and for the next semester. We have some memory locations called registers. Okay? Every microprocessor has registers, even as of today, but they have more registers than we have in our Motorola microprocessor. Okay? Then registers are also the primary places where all the operations of the microprocessor happens, like all these additions, you know what I'm saying? Subtractions or whatever you do, this happens, most of those arithmetic operations. So these are some basic registers that we have in the microprocessor. The first register we have here is called accumulator A. Second one, accumulator B. Then we have one called index register X. Then we have one called index stack pointer SP. Then we have program counter PC. Then we have condition code register. You may not know these registers, right? This is the first time probably you have seen it. So don't worry, because that's normal in this class. And you probably don't know the purpose of most of these registers at this point. Okay? Now at this point, we'll not be talking about the purpose of all these registers, but over the semester, in different times, we'll talk about these, we'll get back to these, we'll talk about, you know, their purpose. But we still want to understand a little bit. So if you look at the registers, you probably have seen there are differences in the length, right? Some of the registers, for example, the accumulators are 1 byte long, but some of the registers are 2 byte long, right? Do you see it? Index register, stack pointer, program counter, those are 2 byte long. And some of the registers like accumulator A and B and condition code registers are 1 byte long. Now, this is why it's like this. It's actually how it was designed, right? But there is a reason why it was designed like this. Whenever the register is 1 byte long, it's most likely that those register will actually work with the data. Remember, the data bus is 8-bit. So whenever you see a register which is 1 byte long, that means that most likely will work with data. Okay? It's probably not true for every time, but most of the time. Whenever you see the register is 2 byte long, that means they're intended to work with the address, because the addresses are 2 byte long. It's really funny a little bit, because the data is the one which are most important to us, but the addresses are sort of like longer than data, right? Because we need more addresses, and that's why we end up having like 16 lines of addressings, right? And only to manage 8-bit of data, every data location. It's a little bit funny, and sometimes it's hard to accept it at the beginning, but that's the case. So we'll talk about all these registers and accumulators for this whole semester, for next semester, for every time we talk about the microprocessor. Okay. Now, we'll try to give you a very basic introduction to programming, low-level language. We'll not probably start the low-level language right now, but probably we'll start it very soon. Now, this is how the low-level language looks like. I'm not saying that we'll understand all of this right now, but I'm trying to give you an idea that how those look like. For an example, you are just saying load 02 into accumulator A. Remember, we have a register accumulator A, right? These instructions means load into accumulator A. And the next instruction tells add 3 with accumulator A. That means you are just doing add 2 plus 3, right? After this addition, you will have 5 in your accumulator A because you added 2 plus 3, right? And then you said store these to a memory location. So basically, this is exactly how things work. So basic, but you will probably never realize when you are working with the high-level language or C++, Java, scripting, okay? But at the end, no matter you're writing your program in C++, no matter you're writing in Java or high scripting languages, at the end, all the programs, every single thing that you are running in your computer, in your cell phones, those get decoded into low-level language like this. And at that point, your microprocessor actually understands what it is reading, and it actually executes this. So it's pretty much like for every single addition, it might be running like 5, 7, 8, or 10 lines or 20 lines of instructions for you. There are plenty. I'm saying for every single day, you might be running at least like hundred thousands of lines of instructions for your microprocessor. You may not even realize it, okay? Every time you click something in the mouse, monitor, I'm saying computer, cell phones, you are actually spending a bit of speed from the microprocessor, because every single thing it runs, you are, consuming the speed of the microprocessor. Okay? Now, again, let's get back to very basic. Since, again, we are very beginner, we don't have any idea how things work here. So, every instruction in the low-level language in this class will have two different components. Okay? The first component is called opcode, which will look like a combination of letters. I'm saying, for an example, it's written LDAA, right? And the second part is called operand. In the operand, most likely you will have a number, some sort of number written, okay, because that's like the data or an address. So most of the instructions will have two different components. Now, again, every time we're writing in instructions, microprocessor decodes the instruction. Remember, no matter you are writing instruction, no matter how you're writing it, at the end of the day, everything you write are actually raw binary, right? In computer, everything is binary. All the instructions you are writing in binary, okay? So that means even if you're writing LDAA02, those actually get decoded into binary. But in this class, even if we know that the microprocessor deals everything as binary, we do not write everything in binary. Instead, we write everything in hex. Why? Because the hex is shorter. It saves a lot of space. For an example, think about this. We actually wrote this in hex. Remember, the default number system for this class is hex. If I write a number, if I don't tell what is the number system, that is hex. If it is something else, I will mention. Okay? Now, for an example, the 8602 is a code, but this is in hex. But remember, in computer, this will be in binary. But we are not. We are writing in hex, because think about this hex. How long it will be in binary? 8602. How long? Like how many bits? 16-bit, right? Remember, for every hex digit, we have 4 bits. So 8602, 8602 will take 16 bits. I'm saying, if you write 16 bits, that will be long, so we just wrote it in hex. Okay? But remember, that's always in binary. Okay? Now, every instructions we write, those have some modes. Okay? Now, we don't exactly understand what is the purpose of these modes yet. Don't worry if we don't understand it. But in this class today, we'll just try to understand only to see whether we can identify the mood of the instruction based on how they look like. Okay? For an example, we have actually 6 addressing modes. But at this point, at the very beginning, we'll be just talking about the first 4 addressing modes. Okay? Immediate, direct, extended, and inherent. Okay? So the idea is, just by looking at the instructions, even if we don't know what it is, even if we don't know how it works, we'll be able to identify the addressing mode. That's it. Okay? We'll just make one single step at a time. We don't understand the instruction yet. Okay? Every single instruction you will see in this lecture, you will see the quiz for this lecture, you will not understand the instruction. So pretty much you don't know what the purpose of the instruction. But you will be able to tell, okay, this instruction is immediate. That means the mode of this instruction is immediate, or the mode of this instruction is extended, okay? Or the mode of this instruction is direct. Just looking at the instruction will give you some hint or information so that you can identify the addressing mode, okay? Even if you don't understand the instructions. For an example, as I said, most of the instructions has 2 parts, right? So the immediate is probably the easiest to identify, because if your instruction is immediate, the operand always starts with a pound sign. Very simple. See, here, you see the operand part? See, you see the operand, right? It starts with a pound sign, right? All of this starts with a pound sign, which is actually very simple to identify. As long as you have a pound sign, you know for sure that's immediate. Probably easiest, right? Now, direct does not have the pound sign. So no way there will be any pound sign. So that means in the direct instruction, you will have an operand without the pound sign. So no pound sign. And also one more thing, that the operand you will have must be 1 byte long or lesser. That means, look at this one. You see there is a dollar sign, right? Now let me tell you also this. Anytime you see a dollar sign, that means the following number is in hex. Dollar sign indicates that the number we are writing after the dollar sign is actually in hex. That's what I'm saying. There is another symbol like this one, which is a percentage sign. Anytime we are writing a number following the percentage sign, that means the number is actually written in binary. That's what I'm saying. The number you are writing is in binary. And anytime you don't see anything, that means, see, there is no dollar sign, there is no pound sign, right? That means 162 is actually decimal. So basically, in the instruction, you can write binary, you can write decimal, you can write hex. Now, for microprocessor, it doesn't matter because it understands all of it. But make sure you use the right prefix. Dollar is for hex, okay? Percentage is for binary. No dollar, no percentage means decimal. Now, the reason I'm telling this because it helps you to identify how long it is, right? For an example, since this is hex, you can tell this is 8-bit, right? Because every hex digit is 4-bit. So this is 8-bit, which is fine, right? Remember I said it has to be 1 byte in direct, right? Now here, look at this one as well. This is pound sign, right? I'm saying the percentage sign. That means the following number is in binary. Now, how long it can be in binary to be 1 byte? 8-bit, right? Now, how many bits you have here? 3, 4 is 8, right? So it can be even less, which is fine, but it cannot be more than 8-bit. Because if it is more than 8-bit, that's more than 1 byte, which cannot be, which cannot fit with direct, right? Now this is 162. Now how do I know this is 1 byte or 2 byte? Because this is decimal, right? How do I know it? Of course you can convert, but there is another small, I'm saying quick thing. All the unsigned, do you remember the unsigned and signed numbers? We talked in digital circuit class. All the unsigned numbers can be at max 255 to be 1 byte. Because you can write 255 when you have all 8 ones. Because in 8-bit, if you have 8 ones, that's the maximum number you can write, right? Which is actually 255 unsigned. So that means as long as this is 255 or less in decimal, it's 1 byte. I'm saying, again, you can always convert, but this is very easy. Just look at the binary decimal number. If it is 255 or less, it's actually 1 byte. So since this is 162, this is 1 byte. Now, extended, again, extended and direct are pretty close, okay? Extended also do not have the pound sign, but this time your operand will be more than 1 byte. That means it will be 2 byte or between 1 and 2, okay? For an example, you see this one, this is 2 byte, right? Look at this one in hex. D123, there are 4 digits in hex. That means 16-bit in binary, right? Now look at this binary. This is more than 8-bit for sure, right? So that means this is 2 byte. And look at this number in decimal. How do I know this is 2 byte or more? It's over 255. It's also it should be less than. It should be also less than 64,536. Okay, because if you have 16 ones, that is 64,535, I think. Okay, so if as long as the number is this number is what 53,539, which is less than 64,535, right? So that is less than 2 byte. but more than 1 byte, right? Because if it is more than 255, it's more than 1 byte, which is fine. Okay. How do I know 64,535? If you have 16 ones, then check the 16 one. Then you'll see the 64,500. I'm sorry, it's 65,535. Okay. If you just have 16 ones, that's 65,535. There is a last one. I'm saying the out of 4. This is called inherent addressing. Inherent addressing is also very easy to identify because inherent addressing doesn't have any operand. You see, these are all opcode, right? So there is no operand, which is very easy to identify because as long as you don't see the operand, that's inherent. Okay. Now, let's try some quizzes, very quick quizzes, and see whether we can identify the addressing mode. Now, in every question, we are given an instruction. We don't understand it, but just by looking at the instruction, can you tell what is the addressing mode? What is this one? Immediate, right? Very easy because it has pound sign, right? Very simple. How about this one? It's not immediate for sure, right? It's not inherent for sure because it has operand. So it can be direct or extended. What is this? It's actually direct. Remember the difference between the direct and extended is 1 byte and 2 byte, right? 35 is actually 1 byte, right? Remember, 35 is what? Decimal, right? Because there is no pound, there is no dollar sign, there is no percentage sign. So make sure you know what is the number system. This is 35 written in decimal. So this is also less than 1 byte. I'm saying it's 1 byte basically. What is this one? This instruction? Inherent, very simple because no operand. How about these? It's of course extended because there is no pound sign. So it's not immediate, it cannot be inherent. So, and then the data, I'm saying the operand we have is more than 1 byte, right? So which is extended, of course. How about these? This is extended because remember, okay, first of all, operand is written in what? Decimal, right? If it is more than 255, it's 2 byte. It's actually a little bit more than 255, right? Just past 255, so it's actually 2 byte. So basically it's extended. How about this one? NEG 29. We don't understand the instruction, but just by looking at this one, it looks like it should be direct, right? But there are some exceptions. This actually is extended. Now let me tell you why this is different, because you might be wondering, we learned all these techniques, now we have some exceptions. Now this is why we have some exceptions. Let me show you something. So I'm here in pause right now. So we have a set of instruction provided to us by Motorola, which is located under the lab section. You see the set of instruction here? There's actually a PDF file. You will need this set of instruction every time you do any quiz, every time you do a test, every time you talk to me. This is so important, okay? We probably need it more than anything in this class. Now let me show you what we have here. This is a 6-page document. We have the soft copy here. I'll give you the hard copy soon, okay? Now, this document have list of all the instructions our microprocessor understand. Okay? Now, this is called set of instruction. Now, every microprocessor, even if it is an Intel microprocessor, it is another microprocessor, every microprocessor has an instruction set it can understand. That's what I'm saying? Now, the microprocessor that we have in front of you inside your computer has even more instructions than we have here. Okay? But we'll be limiting with only with these because, for the whole this semester, we'll actually try to understand this one single document because there are so many information here. Okay? Now, all the instructions that we have seen on that page are actually here, coming from here. There are even more than here, plenty of instructions. Okay? Now remember, what was the instruction then? NEG, right? Before you answer and identify any addressing mode, you always should check this document. Now, why is this? For an example, What this instruction set tells you that, for an example, every instruction, for an example, if you take this one, ABCA, it actually tells how many different addressing mode it can have. This means immediate, right?
Yeah.
This means direct, this means extended, right? So that means it can have direct, it can have extended, it can have immediate. Now some instructions has limitations. There are reasons for it. We probably will not understand the reason right now, but at some point we'll talk about these. But some instructions has limitations. So for an example, remember the instructions we were talking about, NEG, right? Let me find NEG here. Let me find NEG now. Here is my NEG, okay? Look at this NEG. Do you see it? This was the NEG instruction, right? Look at the addressing mode it supports. Now, do you see it doesn't support direct? There is no DIR here, right? So whenever you have an instruction like this, even if the answer is direct, you always should check this one. If you don't see direct on the list, that means it doesn't support direct. So it will be by default extended. So in case of direct, there are some exceptions. Meaning even if it is direct, always double check with this instruction set. If you don't see direct on the list, it must be extended. That only happens in case of direct, because some of the instructions do not have the direct mode, and there is a specific reason for it. Okay, we'll talk about this, but I'm trying to give you a little bit of hints. Remember, I was just telling the instruction bus is 16-bit and data bus is 8-bit. Whenever you see an instruction, it doesn't have the direct mode, that means it doesn't actually work with the data, it works with the instruction. Because the extended is 16-bit, right? I'm trying to give you an idea, but we'll talk about this in future. So for sure. So I'll give this document to you, print out of this document today, but before that you can even start with the quizzes, so that, because you have the soft copy, you can always find even easier in soft copies than hard copies, right? Let's go back to the presentation. So make sure you know these, that some of the instructions do not have the direct addressing mode, okay? So that's why if the answer is direct, you should always double check. If it doesn't have direct on the list, it will be extended. So these are exceptions, okay? Any question? So if not, then we should be ready for our very first quiz of this class. In the quiz, you'll pretty much see the questions that you've seen here. So in every question, you'll be given an instruction. All you have to tell is what is the addressing mode. We have 6 addressing mode, but we are just talking about the first 4 right now. So all the answers will be, out of one of the 4. Okay? Let me stop this presentation here, and let's go to the quiz 1, and let's try this quiz. And again, you will need the instruction set, and which is located under the lab section.